Hi everybody, so I wanted to make a recording of the applied calculations lecture so that you could go back over it so I can make sure there weren't any errors that I might have done live to make sure that it's all there for you, correctly done, and you can review it over and over if you'd like. Remember, the key to doing well in the exam with the calculation problems is knowing your calculator, knowing the calculation equation sheet, and also practicing the questions over and changing the numbers within them so that they become new in a way, kind of a new approach to it so that you can understand how you would do it on an exam. Because what happens during the exam is usually students think they know the practice problems, they do really well, but then you get a new one on the exam, even though it's pretty much the same type of problems I always give, but the numbers are different, and that really trips up students. So that would be how I would practice it. So I would do that as you go over this lecture as well. And you can see the objectives of this class is to get you familiar with the equation sheet and all the equations and go over some practice problems. So this first problem really isn't an equation sheet problem per se, but it's to go over a concept from the previous lecture regarding kinetic type. When we learned about two kinetic types in the first lecture for this course, one being linear and one being nonlinear, and their definitions or how they look is in the name, linear versus nonlinear. So let's see, you looked up two new antibiotics in a package insert in this problem, and you want to figure out what the kinetics are for each one. So what we can do is actually do that graphically. Let's see if we can figure that out. So we'll make a graph, okay? And it looks like we have doses that run from 0 to 1,000. So let's call it 250, 500, 750, and 1,000. And then we have concentrations that run from, one's a little bit lower on antibiotic 1 and one's a little bit higher on antibiotic 2, but we'll put them on the same graph, even though that's probably not the best thing to do. And we'll call it to about 500. So let's put 100, 200, 300, 400, and 500. And of course, we should label our axes. This is concentration. I apologize. I'll try to write more clearly. And that's dose. And for antibiotic 1, at a dose of 100, we have a concentration very low, probably around 15, which is way down here. And then at dose of 250, it goes up a wee bit to 37.5. And then at a dose of 500, it goes up to 75. And then at a dose of 1,000, it goes up to a whopping 150. And you can see what it looks like. There you go. So if you had to take a guess already what it might be, you might, if you had to take a stab in the dark, you maybe say it was linear. But let's see what antibiotic 2 is, and we'll make that in red. At a dose of 0, obviously. At a dose of 100, it looks like we're looking at 25, so a little bit above here. All right. And then a dose of 250, we're looking at 62.5, so probably double the other one, right? And then at the dose of 500, we're looking at 190, which is up here. So going up rapidly. I apologize, I'm trying to fix my pen. I don't know why it keeps pulling that up on me. And then 510 for the last dose at 1,000. So way up here. So if we had to take what that looks like, that's starting to go way up there. So that one looks pretty nonlinear if you ask me, right? So the first one's probably linear, antibiotic 1, right? The second one is nonlinear. And which type is it from the last one? Is it saturable or Michaelis-Menten? We're probably looking at Michaelis-Menten, right? Because Michaelis-Menten is where you increase the dose and it goes up more than expected. And I also did them within an Excel sheet to show you what it looks like. And you can see when you change the scales to the actual problem, or at least the graph, it looks much better. So antibiotic 1 does look linear, and antibiotic 2 looks non-linear. But it actually, when you put it in an Excel sheet, it actually looks like this portion is probably Michaelis-Menten. Well, this portion is maybe linear or more likely saturable. So it's a weird mix of a drug, which is possible, but it's not really something we talk about in this course very much. But interesting nonetheless. Now it's the part of the lecture where we get into actually starting to use the equation sheet. And the first one here is a basic problem. So you have this drug that's called XPT 101. We want to figure out what exactly would be a maintenance dose and a loading dose in 3 different types of patients: healthy subjects, patients with liver failure, and patients with heart failure. And we want to know what those doses would be to achieve a steady state concentration of 10 milligrams per liter. And you can see we're going to be utilizing all of these PK parameters for each one. So let's go ahead and do that, starting in the next slide. Now for each of these, we will go over each of the calculations we're going to do within each of the scenarios at one time. You'll see what I mean in a second. So again, we're going to break this up into 3 sections. So first is healthy. In this second column here, we'll do liver failure patients and heart failure patients. You can see they have specific pharmacokinetic parameters that, if you really want to think about it, probably makes sense. You have lower clearance with liver failure because your liver isn't processing the drug. Or if you have heart failure, perhaps you have a higher clearance due to other various factors, maybe how the drug partitions and things like that. So let's do the calculations. What are the loading doses and maintenance doses for each of these? So they can be found on page 4, which is we are looking at IV bolus, maintenance dose, and loading dose. So let's calculate loading dose first. So if you look at the equation sheet, loading dose is equal to volume of distribution times concentration. Steady state that is desired. And so for this patient here, we can see the volume of distribution is right up there, 175 liters. And we know from the previous slide that we are shooting for a 10 milligram per liter steady state. And that's pretty easy math to do, right in your head. 1750, the liters cross out, and that's milligrams. So there's your loading dose for that. If we do the same thing over here, we get 300 liters times 10 milligrams per liter. Those cross out, and that gives us 3,000 milligrams, And then finally, if we do our calculation here for the heart failure patient, we're looking at 100 liters times 10. So you can see the loading dose differences between the 3. The healthy patient gets the one in between. The liver patient gets a higher dose. The heart failure patient gets a lower dose. What about maintenance dose? Well, maintenance dose off of that equation sheet area is equal to clearance times concentration at steady state, which if we get the clearance from up here, we can do 45 liters per hour times 10 milligrams per liter. This time the liters cancel out, and that gives us 450. It's just multiplied by 10, so it's pretty straightforward. Milligrams per hour. If we do the same thing here, I won't do all the units this time, but it's going to be 15 times 10. So 150. And this one's going to be 30 times 10. 300. milligrams per hour, and milligrams per hour. So you can see it's a little interesting too. So the 450, because this patient has a superior clearance, the healthy patient does, they get a higher dose. The liver failure patient actually has, makes the marks there, sorry, the least amount of clearance, so they get the lowest amount of drug per hour. And then the heart failure patient has kind of middle of the road there. One last thing I want to calculate is half-life. And so half-life in this scenario, we know if we look it up on our equation sheet, it's 0.693 over KE. But we also know from the equation sheet, if you look on that first page, that KE is equal to CL over V. So if we substitute this in, we get T1/2 is equal to 0.693 times V all over clearance. All right. Then if we plug those in, right, you're going to plug in the numbers here. I'll just do this first one. 693 times the volume of distribution, which is 175 liters, over 45 liters per hour. Liters obviously cancel out. It bumps the hours up to the top. And that will give us approximately 2.7 hour half-life in a healthy patient. And why is this really useful? Because it helps us to figure out steady state, right? If you need 3 to 5 half-lives for a steady state, to get to steady state, that means this is going to be around what? Maybe about 12 hours before this patient reaches steady state. And so you could do these calculations. I'll let those you do those on your own. But you can do that half-life calculation for the other two and compare and contrast what would be the half-life for these other two scenarios, and then juxtapose that to what the doses and the loading dose are. Remember from our first lecture that loading dose is completely dependent on the vessel it's being put into, so the volume of distribution. Well, maintenance dose is dependent on the clearance, the rate at which the body removes the drug. So there you go. There's a basic equation and a basic problem that we've now covered. Moving on to our next problem, we're going to figure out how to do bioavailability. And this is a concept that you need to know. It'll be on the boards, maybe not necessarily the calculations, but just what bioavailability is. And to review that, it is what we compare when we have something in the blood versus taking it in another route. And that other route can be oral, it could be dermal, it could be sublingual, it can be anything, it can be intranasal. And so bioavailability means how much of it gets into the blood. If we give something IV, it's always going to get what? 100% into the blood, right? Versus everything else gets taken out by first pass metabolism or absorption rates or something like that. And less of it gets into the blood. So we want to know what that is. And usually that's called, the factor is called F, or bioavailability. And it ranges from 0 to 100% getting into the blood. So let's do some calculations here. We have a new drug here that's been studied for renal transplants, and you can see they figured out all the following information based on 3 different versions of this drug with the AUCs here. And so we want to figure out what is the bioavailability of the oral capsule and oral liquid, and what is the relative bioavailability of the oral capsule compared to the oral liquid. So we would use the equation found on number 2, page 2, and that would be under the relative bioavailability definition. Okay, that's what we want to use. And that's basically, it's just a fraction. So for this first part here, how would we solve it? We are going to do each of these, the oral capsule and the oral liquid. I'll call it F for bioavailability. And we need to do that basic fraction. And what always goes on the bottom, it's always the IV for these scenarios where you want to figure out the true bioavailability. So to do that for each of these, we can insert the AUC for the intravenous version, 1530, An F, or bioavailability, is always unitless because the units cross out, so I won't even put them in there. Okay? And if we're going to do the capsule, we would put the capsule AUC up here, which is 1220. And we put the liquid AUC here, which is 1420. You already can tell the liquid has a higher bioavailability, and that should check out right now. When you do the math, you get around 0.8 or 80% bioavailable. And for the liquid, it's about 0.93 or 93% bioavailable. So now, if you want to do the relative bioavailability, you're just doing it relative. It's asking you to do the oral capsule compared to the oral liquid. So for the relative portion, we're going to do capsule over liquid. The liquid is 1420 over the capsule is 1220. And that math works out to be approximately 0.86 or 86%. And so you can tell, again, we already knew this from the first calculation, that the liquid is more bioavailable than a capsule. And if you do it relative to each other, the capsule is 86% bioavailable as compared to the liquid. So that's pretty easy to do bioavailability calculations, but something that you should know and a concept that you should know definitely for the boards. All right, so with our next example here, it's going to be an intravenous bolus. So in this example, a patient is given a 400 milligram dose over 20 minutes, so it's a relatively short amount of time, so we're going to call it a bolus. Their volume of distribution is 30. Their KE is 0.115. I want to compute the half-life and compute the expected concentration 4 hours after that dose was given. All right, so let's first start with half-life. So half-life, again, that one's found on page 1. It's the first one. So half-life, and you'll do this calculation a quadrillion times, so get used to it. Is 6.93 over KE. Hours to the -1. That scooches the hours up to the top, and that gives you around a half-life of 6.0 hours. What information does that tell you? That tells you it's going to take the patient about a day or so of dosing to get to steady state, right? So now we need to figure out, if we want to compute the expected concentration 4 hours after the dose was given, we first have to figure out what is the post-dose concentration. And so you can find that equation on page 2. It's under the IV bolus single dose section. And what we want to do is calculate C naught. So that initial concentration is what we're looking for. And so we do that with D over V. Pretty simple. And so this would be 400 milligrams over the volume of distribution, which is 30 liters. And that gives you a post-dose concentration of approximately 13.3 milligrams per liter. So that's what we know the dose is right after you give the patient, or the concentration is right after you give the patient a dose. Okay? So now we need to figure out what that concentration is 4 hours after immediately post-dose concentration. How you do that? That is going to be C equals C naught. In this case, this could be any concentration here. E to the minus KET, where T is the time we're looking for. So we're going to put 4 here for 4 hours. And so now we just plug and chug. Then E to the minus KET, so 0.115 times the time we're shooting for, 4 hours. Okay? And if we do all that math out, we get somewhere around 8.4 milligrams per liter because it captures this concentration. And again, I explained this a little bit in the live version of the class, but everything we do in this class, so that we don't have to do fancy integrals, is on a line. It's on a straight line. So you can do rise over run. That's all we're doing. We're figuring out, that's a bad rise over run. Let me redo that. We're just figuring out how we can move up and down a line. So run, rise, okay? That's how we have to move. And we learned from high school, it's mx plus b. But here we move up and down the line because we're turning a complex line into a simple line using these exponents. And so when we want to go down a concentration line, it's e to the minus KET, okay? And when we want to move up the line, meaning we want to get a previous concentration, we divide by e to the minus KET. So this one's multiply, this one's divide. So in the future, when we need to calculate a concentration that we want to know that was previous, we divide by e to the minus KET. When we want to calculate a future concentration, we multiply by e to the minus KET. So that's a good concept, just keep in your mind, kind of makes sense of why we use all these messy exponents to figure out things. But the answer we're looking for here is through these kind of relatively simple math. It's a little higher level equation, but not as messy as some of the equations that we'll see shortly. Now I wanted to go over an example here where we're going to do some of the quote-unquote calculations, but just from a graph instead of doing it with equations, just so you can understand why we use the equations, how they're actually based on the graphical form, but we just use equations. So some students' minds work a little better when they think about the graph, and that's the reason I show this one. So find the T1 half of this drug. So it looks like it's a loading dose, 600 milligrams over a period of 1 hour, and then they took some concentrations over 6 hours. And so how would one find the half-life? Well, pretty simple, right? You look for a concentration and you see what half the concentration is and how long it took, approximately, right? So 15, 7.5, 4 hours. And that checks out with here as well. So you have 12.6 and 1.3. How many hours did it take to get from that to that, which is half the concentration? Again, that's 4 hours. Okay? So very good. So that's how you start with determining the half-life from a graph. And then we can go back to just doing all the calculations we've already done multiple times in these slides. I told you to do this one a lot. In this one, we're just inverting our half-life calculation to calculate KE, which comes out to be approximately 1.73 days to the -1, right? Because the time is days. So make sure you get your units correct. And finally, because we have an initial concentration, or a C naught here, we can figure out what the volume of distribution is. Because where does this come again? Where does volume distribution come in? We just learned a few slides ago. Loading dose. It's all dependent on loading dose. Because when we do a loading dose, we're only worried about how big that vessel is. We're not worried about the drug being cleared yet. So we can do volume of distribution by dose over C naught. We have a 600 milligram dose over a C naught of 15 milligrams per liter. And that gives us a volume of distribution of about 40 liters. The milligrams cancel out, the liter scooches up to the top, and there you go. So that's pretty easy how we can use a graph and to find the initial half-life, which then allows us to derive these relatively basic equations. But now let's do the previous slides concentrations and do them without the graph. So how would one determine KE if you didn't know, or you didn't have these perfect, let's assume you didn't have these perfect half concentrations. Assume they weren't, okay? You can actually calculate KE with an equation. And that equation is found on page 1, okay, under the KE parameter. And it's equal to negative ln of whatever concentration using, the first concentration and the second concentration, divided by T1 over T2. And you always have to make sure your concentration and your times match up. Now you can see here, or from the previous slide, that we have lots of concentrations we could use. We could do this in multiple different ways. Doesn't matter. We could do it from the 0 to 1 hour. We could do it from the 4 to 1 hour. We could do it from the 5 to 4 hour. It doesn't make a difference. I encourage you to do all those calculations and see how close the number matches up. It's pretty darn close. There's a little bit of difference there. There's always wiggle room in these calculations, but they're all approximately equal to the same KE. So let's do the concentration with C naught. Let's do it with this one here. I'll just circle it up here. C naught, and let's do it with C1. So let's just take the two next to each other. Let's make our lives easy, right? So ln of 15 minus ln of 12.6 divided by, and this is the time part where we got to figure it out. This is 0 minus 1. I know it's weird to have a 0 in there, but that's the way it happens. When you do that math in, and this is the opportunity to make sure you get used to your calculator with all these exponentials or natural logs. If you do that math, you're going to get approximately 0.173 hours to the negative 1. And remember, a KE always has some sort of time unit to the negative 1, because that is what the elimination rate constant is. So you can check that out again with any other pairing you want to do here. Check that out and see how close it comes to about 1.17. It's going to be pretty darn close. All right, going back to the calculation we've already done 17 times. I'm just going to write it out here real quick. I'm not going to spend time on it. 0.693 over KE. And that's going to give you an answer around 4.1 hours. Very good. How would we compute volume of distribution? Well, we would do it like we did in the previous slide. So that's just D over C naught. We already did that in the previous slide. And so no need to show it again here. You can look at the previous slide. But let's say we want to figure out what the heck the concentration was 6 hours post-dose. So you can find that equation, which we've already covered in a previous slide, on page, not 6, why did I write 6? 2. Okay, intravenous bolus, single dose. All right, and it's a pretty easy one, right? Because if we want to figure out the concentration in 6 hours after giving the dose, then we would go ahead and do C something. And if we want to make it easy, we'd probably do C naught, right? Times e to the minus KET. Remember, we're moving down that line to figure out what the concentration is. So that's 15 milligrams per liter times e to the minus KE. KE we figured out up there was 1.73 hours to the negative 1 times time, which is 6 hours. Okay, those units cancel out because you would expect them to. And that gives you a concentration of about 5.4 milligrams per liter at 6 hours, which makes sense because if we look at the concentration at 5 hours up here, it's 6.3. So we'd expect it to be slightly lower than that. Okay? So you can see here, we can take that one step further from the previous slide where we can actually start to calculate any concentration. Okay, now let's figure out and do a little more complex of problem. A multi-part problem where we're figuring out concentration at various times under steady state, not under steady state. We're going to have a continuous infusion here, 60 milligrams per hour, and there's PK parameters. So first it wants us to figure out what's the serum drug concentration of drug A in this patient after receiving the drug for 8 hours versus at steady state. So that should be key to you. That 8 hours probably isn't at steady state, but we can understand that by doing a quick calculation, which we've done now 17 million times. I like to just make that up. We do it a lot. That's my point. So don't ever get a half-life equation question wrong, please. Please. So when you do that math out using KE equals 0.139, you get a half-life of right around 5 hours. It's 4.9, but it rounds up to 5 hours. Okay, so what does that mean? Steady state is achieved at somewhere around 20 hours, so nearly a day. So are they at steady state when they have an 8-hour dose? Nope, the answer is no. Okay, so we have to go to the equation sheet and use a single dose equation, which is found on page 2. And so that single dose equation looks like this. C equals K naught over KE times V times 1 minus e to the minus KET, because we're not at steady state, so it becomes a little more complicated. Okay? So if we want to calculate this out, plug everything in, we got 60 milligrams per hour over 0.139 hours to the negative 1 times V, which is 40 liters And that's all multiplied by 1 to the minus 1 minus e to the negative ket. So 0.139 hours to the negative 1 times, and what's the time we're looking for? 8 hours, right? So 8 hours. Okay? Put lots of parentheses here. Cross out our units. What else crosses out? Get rid of this. Let me correct that here. This is milligrams per hour. We get rid of this. We keep liter, right? Because it's a concentration. A concentration is always grams or milligrams, usually over some sort of measure of liquid. So milliliters or liters. If you do all that math out, then you're going to get approximately 7.2 milligrams per liter. And that is what we would expect the concentration to be 8 hours post a single dose that has not achieved steady state. And when you do this math, I would probably do this section alone in your calculator and maybe write that number down, and do up here alone and write that down in your calculator, and then do this, and then multiply them together. You probably want to do it in steps and try to put all this messy stuff into your calculator in one shot. It's not a good idea. So do not do that. Okay? So what else does it ask? It asks, what's the concentration at steady state? And so that is also on page 2. And concentration at steady state is a little more straightforward for us here. It can equal K naught over CL. We don't have CL, right? So then we have to plug in KeV. And if you do that math, you get around 10.8 milligrams per liter. So you can tell 8 hours after the dose, not quite to steady state. It doesn't reach it until, again, 20 hours or so on the drug, and it increases from 7.2 to 10.8 milligrams per liter. Okay, the next part of the problem asks, is it possible to compute the drug A concentration 6 hours after stopping the initial 8-hour infusions? It sure is. We're back to our e to the minus ket. We already figured out what that concentration is at 8 hours. So we would make this C 6 hour, but post 8-hour dose to be specific. So you put that 8-hour dose in here, 7.2 milligrams per liter, e to the minus ket, which is 0.139 hours to the negative 1 times t, and in this case it's 6 hour. The hours cancel out. Do all that math up, and should it be a higher or a lower dose? It should be a lower dose, right? Because we stopped the infusion. We want to see what it is 6 hours later, and we can see that it's approximately 3.1 milligrams per liter, and that checks out, at least in our brain, because it should be lower, right? Because we're going down the concentration line. This was your C1, and this is your C2. But wait, there's more. Now it wants you to assume it ran until steady state was achieved, which we determined up here as 10.8. So what would the serum concentration be 6 hours after that infusion was ended? So 6 hour post steady state. Now, the only difference here is you're inserting 10.8 milligrams per liter, e to the minus ket, right? Multiplying that out. Won't write it all back in there again. But if you do it, it's approximately the same math, and it should be what? A higher or lower concentration than this previous question of 3.1. Should be slightly higher because we're starting with a higher concentration. So 4.6 milligrams per liter, and there you go. So you can see the differences of, in this continuous infusion example, of when one achieves steady state, when you don't achieve steady state, and how that'll affect future concentrations. Okay, so we've done a bunch of calculations with various IV scenarios. What about an extravascular drug? So an oral drug, right? You can do the same thing. If you have strong enough PK parameters on oral drugs, you can theoretically calculate concentrations as well. So on this one, we have 750 milligrams of oral drug given with 2 concentrations measured. The first one you can see there, and the second one with the times. So let's calculate Ke. Ke uses that little bit messy equation, minus ln CO1 ln C2 over T1 minus T2. We plug all that in. Ln of C1 is 51.9 minus ln of C2 of 21.3 over 6 minus 24. And you can tell why the minus sign is there, because somehow you're going to end up with negative either in the numerator or denominator, because you could actually use the concentrations in reverse here, which would make the bottom section here positive and the top negative. So that's why there's always a negative there. If you get a negative Ke value in your calculation, you did it wrong. That's why all of our other calculations we use in this class are e to the minus Ket. So you wouldn't have a double negative there. So I'm just explaining why there's a negative in this calculation. So if you plug all that in, we're going to have a Ke approximately of 0.049 hours to the negative 1. And we'll do the half-life calculation that we've done now many times over Ke. Plug that in down here, and you'd get approximately 14 hours. So that's a pretty long half-life for a drug, huh? But that makes sense for an oral drug. Many drugs are dosed twice daily, so maybe this one's dosed twice daily. And for the second part of the problem, it wants us, or third part I should say, it wants to calculate C naught. So what are we doing to figure out C naught? Let's go back to our trusty graph here. So we have a C1 and a C2. C naught is the beginning, right? So we got to go up the curve. So remember what we do with that? We multiply a concentration. We don't multiply a concentration. We divide a concentration. We divide a concentration to make the concentration get bigger. So C naught is equal to, let's do C1, divided by e to the minus Ket. C1 is 51.9 milligrams per liter, divided by e to the minus 0.049, something we determined above. Hours negative 1 times 6 hours, because that's time 1. Okay? When you do out that math, if you make it just a nice round number, we're looking at around 70 milligrams per liter. And that checks out in our head because we'd expect a higher concentration for C naught, or initial concentration. Okay? Finally, we want to calculate the V over F hybrid value. Why is it called hybrid? Because I didn't give you F. We don't know what F is. But we have to include F because it's an extravascular drug. So there is some sort of bioavailability component in there. We're going to use the same equation we did before, and I guess I didn't put the equations up there. We're looking at equations on page 1 for Ke and half-life, and we're looking on page 2 for the extravascular post-absorption, post-distribution equation. So you can mark that down. We're going to be doing for the hybrid value, if it was C naught is equal to FD over V, we would then change that to V over F, that's the hybrid value, is equal to D over C naught. We do out that math, D over C naught, 750, right, milligrams over, let's call C naught around 70 milligrams per liter, and the milligrams cancel out, so the V over F is equal to around 10.8 liters, okay? And so what if I had told you F is equal to 80%? If it's 80% or 0.8. So how would you incorporate that into this answer? Then you would just do V equals, you'd have to move the F up there and multiply it, 10.8 times 0.8 is equal to approximately somewhere around 8.6. So the volume of distribution decreases slightly when you incorporate the bioavailability of this specific drug. Moving on to the next problem. This one is looking at an intravenous bolus drug. And so this patient is given 100 milligrams of drug F intravenously until steady state occurs, and they're the PK constant. So we want to figure out what is steady state concentration 23 hours after the last dose, meaning that steady state was achieved. We got to figure out what is the actual concentration 23 hours after a dose. So for this one, you can go to page 3. And if there are slight discrepancies in the page numbers I give you in this lecture, you still should be able to find the equation if you look carefully through the equation sheet. This is going to be on the intravenous bolus section for this steady state. So IV bolus in steady state. So this is a big messy one. So this is a problem where I'm giving you a little bit more math that you have to work with. So what's the concentration of steady state at a given time t? And that's equal to always dose over V gives you the initial concentration, e to the minus k e t on top, over 1 minus e to the negative k e tau. These two are different, okay, versus this. Make sure you note that. What's the difference between t and tau? Tau is the dosing interval, and t is the time we're looking for. So what are we giving in this problem? We're given the D, which is 100 milligrams. We're given KE, we're given V, and we're given time. But there should be something that pops up in your head. You always have to pay attention to units. This is one of the few ways I can trick you on the exam. The time units for KE is days, and the time units for the T is hours. So we have to do something to change that. So generally what I would do is I would change the units of whatever KE is to match across the board here, meaning that I wouldn't change KE itself. I would shoot to change it to what KE is. So since it's days, that's what we're going to do. So for time for 23 hours is how do you multiply that out? You could just kind of figure it out. Most of you probably could do it with a quick calculation, but we'll do the unit analysis so that you understand just a little bit better. And so if it's 1 day over 24 hours times 23 hours, right? Then you can cancel out the hours, and this will give you approximately 0.958 days. This will make sure that your units match in the upcoming equation here. So now, if we do all this math out, 100 milligrams over 75 liters, right? Times, this is where it gets a little bit messy, 1 to the minus 0.116. This is days to the negative 1 times what we just computed, 0.958 days. So they cancel out. That's why we had to convert them. Over 1 minus e to the negative 0.116 days times, and what the heck's tau here? Tau is, it's given daily. So it's 24 hours, which is equal to 1 day, which is equal to 1 day here. That cancels out. Okay, so if we do all that math, we get approximately 1.33 for this portion, and then we get approximately, it looks like 0.895 for the top portion, and 1 minus 0.890. They should be pretty darn close, right? Because it's 0.958 in 1 day. And if we do all that messy math out, and this again, practice this in your calculator, get used to this so you don't mess this up on the exam. You don't want just use of calculator to be the reason you get a problem wrong. But if you do all that math out, you get approximately 10.8 milligrams per liter. So the steady state concentration, 23 hours after the last daily 100 milligram IV bolus dose, is approximately 11 milligrams per liter, or exactly 10.8. And that is how you do this problem with a big messy equation. So key points here, make sure you're converting your units correctly, and also make sure that you can use your calculator well for these more messy equations with multiple exponentials in the top and bottom of fractions. Moving on to the next problem is a similar type of problem where we're looking at an intermittent IV infusion this time. They get 140 milligrams per hour for 1 hour every 8 hours until steady state is achieved. There's PK parameters and wants to know what the steady state concentration immediately after a 1 hour infusion. So very similar to the previous problem. This is going to be on page 3 under the intermittent IV equations. And we're going to be using the steady state equation for it as well. So what does that look like? CSS steady state at what would be considered max, because it's immediately when the infusion ends, is the infusion rate K naught over KEV, all right, times 1 minus e to the negative KET prime over 1 minus e to the negative KE tau. So we already learned what tau was. Probably put tau the other way. I guess I put a J there, huh? Tau. But what is T prime? T prime is specifically for intermittent infusions, and that refers to the length of the infusion. What do we know here? We know the infusion rate, so K naught. We know the T prime, which is 1 hour. We know the tau, which is 8 hours, right? TID. And we know the V, and we know the KE. Checking our units, milligrams, hours, liters, hours. Looking pretty good. Everything's in hours. Nothing sneaky here on my part. Finally, let's go ahead and start to solve this kind of more messy equation. Probably even a little bit more messy than the last one. So K naught is 140 milligrams per hour over KE, which is 0.30 hours to the negative 1, times V is 16 liters. All right, so your hours will end up canceling out, which makes sense because it's going to give us a concentration, times 1 minus e to the negative 0.30 hours to the negative 1, times T prime, which we learned was 1 hour, so just stick a 1 in there, okay, over 1 minus e to the negative 0.3030 hours to the negative 1, times, and what is the tau for this one? It is indeed 8. Alrighty, if you start to do all this math out, you get approximately 29.2 for this first part, and then you get 1 minus 0.741 over 1 minus 0.091. Okay, then when you do all that messy math out, again, this is where you get your calculator skills together. You get 8.3 milligrams per liter. So that is what this concentration is for this intermittent infusion immediately when you turn off the infusion. Okay, and that's how we figure that out. CSS max is also what it's generally called. You'll learn about this more in later lectures on aminoglycosides. Here's our last problem where we're going to be computing some concentrations. And so in this one, you can see it's going to be a multi-dose and steady state computation. So we have a patient getting 300 milligrams of drug H intravenously every 6 hours. And he has a pre-dose concentration of 2.5 milligrams per liter and post-dose concentrations of 9.21 hour and 4.55 hours after that second dose is given. What is the elimination rate constant and what is the volume of distribution of drug H for this patient? You can see here, we don't get KE, right? So this is another thing I could do to you on the exam. So how do you do that? Well, we got to use that KE equation that we've done earlier in this lecture. And that looks like this. Remember the negative ln of C1 minus ln of C2 over T1 minus T2. And let's use the two post-dose concentrations because that's what you should stick with. It has to happen after a dose. All right. And if you plug all those in, (1 hour, 5 hour, right? 5 hour. is equal to around 0.108 hours to the -1. Okay, so there you go. We got that done. Pretty easy peasy. And then volume of distribution brings us back to what? Brings us back to, if you go and look at that page 3, intravenous bolus area, because this looks like it's a bolus dose, it's equal to, it always has a dose in it, right? It goes back to that loading dose concept I taught you about where we're worried about volume distribution. And for this one, it's C naught minus C pre-dose. Very good. So here, we at least have some of this information, right? 300 milligrams. Pre-dose is what? It's given 2.5 milligrams per liter. So it's a trough right before the second dose, right? However, we got to figure out what's C naught. What is C naught? It's the concentration immediately after the dose. So it's basically kind of like a C max almost in this scenario. So we can do that. We can back extrapolate, right? We can do that pretty easy. We could do that with either the 9.2 that I've already taught you earlier, the 4.5. Doesn't make a difference. Let's do it with the 9.2. 9.2. And what do we do to back extrapolate? E to the minus KET over it. So 9.2 milligrams per liter over E to the minus, we just figured this out, hours to the -1. And how many hours? It's going to be 1 hour, right? You do all those computations up, it should give you a higher concentration than 9.2, right? And it certainly does. It's 11.1 milligrams per liter. Now we can plug that in. Milligrams per liter. We can do up that math, which is around 34.9 liters. You could round it to 35 if that's what the problem called for. But there you go. And that is how you figure out PK constants for a particular patient given drug levels. And this is very common in inpatient work because you could always use population-based PK parameters, but it might not give you the best drug regimen. So how do you get the best drug regimen? You take some concentrations on the patients, and then you figure out these later, volume distribution and KE, and then you can recraft their drug regimen by essentially using these patient-specific parameters to do that. And so that brings us to our next slide, which is where we use these concentrations to figure out PK parameters to then do therapeutic drug monitoring or basically develop drug regimens, right? And all of this is at the end of your equation sheet, and I believe that is page 4. So let's go ahead and use that page 4 to develop some therapeutic drug regimens. So the first one we'll do is one here on the left, it's continuous infusion. You can see there's the PK parameters. We're using population this time. We haven't determined it from the patient's drug levels, but you could do it that way, like the previous question. And so we need to use continuous infusion. We have a target concentration at steady state, 3 milligrams per liter. And so with a continuous infusion, do you need to determine tau? You sure don't, because it's continuous, right? So that is why it's not in there. So continuous infusions are pretty straightforward. We can see here we'll figure out the infusion rate is K naught. It's equal to concentration at steady state times clearance, which is 3 milligrams per liter times clearance, 1.0 liters per minute. Okay, and we see that we do have units that match, and that should give us approximately 3 milligrams per minute. So we already figured out the first part. Wow, that was easy. Cool. But the doctor wants a loading dose, so let's figure that out too. And what does a loading dose always depend on? Volume of distribution. And what does a maintenance dose always depend on? Clearance. So this one is pretty similar, other than it's just volume of distribution. Which is 50 liters. Pretty easy math again. Liters cross out. And it's just 150 milligram, probably IV bolus for the loading dose. All right, very good. Let's move on over to an example that's a little more messy. Intermittent infusion. Here we have another drug. There's PK parameters. And here, because it's not a continuous infusion, we have to have maxes and mins, right? Because there's maxes when you just end the infusion, and then there's mins right before you begin it. And so therefore, we do need to figure out a tau with this one. If you look at the equation sheet, tau looks like this, ln C1 over C2 over KE plus T prime. You have to incorporate, and for an intermittent infusion, the infusion rate. And a little trick of the trade here, this is also equal to ln of C1 minus C2 over KE plus T prime. If you go back to high school, you'll remember how natural logs work and how they can change back and forth between a natural log minus a natural log can turn into a fraction. Okay, so that's why I wrote it that way originally. You could do it either way. And one other clarification, when I say C1 and C2, I really mean max and min, right? Because that's what we're working with here, max and min. Anyways, so if you input all of that, you're going to get approximately ln, and I'll do the fraction just because it's easier for me to write. Makes my life a little bit easier. 6 over 1 over 0.087 hours to the negative 1 times, or plus, T prime, and it says fused over 1 hour, right? And then KE's in hours, so we can just put 1. So that gives us a tau of 21.6 hours. Now, would you ever tell a nurse, give this drug every 21.6 hours? No, you wouldn't. That's why you round to a reasonable dosing interval. On the test, I tell you to round it to the nearest dosing interval of, for example, 12 hours. So near the nearest 12-hour dosing interval. What would that be for this one? Would it be 12? Would it be 24? Of course, it's 24, so it's a daily dose. All right? So now we can move on to the next equation and figure out maintenance dose for this intermittent dosing scenario, which admittedly is a little unpleasant. So CSS max is equal to K naught V over KEV, K naught over KEV times 1 minus e to the negative KET. Then if we rearrange this so we actually solve for K naught, just showing you how the equations connect from earlier in the equation sheet to get our actual infusion rate or maintenance dose for an intermittent infusion. Then it turns into CSS max times KEV times 1 minus e to the negative KE tau over 1 minus e to the negative KET prime. It's good to know how the equations across the equation sheet are similar and different, and so you should go ahead and look at those two equations and how they are rearranged and match between those third and fourth pages of the equation sheet. If we do all this math out, and I'm going to mostly let you do that just because it's quite a bit of math and I'm running out of space here. We're looking at approximately, right? We have 20 liters up here, so we have a V, we have a KE, we have our CSS max, so that's the first part of this equation. We now know, we also have the KE there, but we know what the tau is, which inserts into this upper part of the equation. The T prime is 1 hour, and so make sure you plug and chug all of that stuff. And if you do all that stuff, kind of the roundabout numbers you get are 6 times 0.087 times 20 times 0.847 over 0.083. Computing that, you get 107 milligrams per hour, right? And so we probably, again, wouldn't tell usually someone to give 107 milligrams, probably round it to something like 110 milligrams per hour. And finally, we want to know a loading dose as well for this scenario, and a loading dose with intermittent IV infusion is equal to K naught over 1 minus e to the negative Ke tau. And note how we had to actually figure out K naught in order to input it into the loading dose for an intermittent infusion. So this is one of those scenarios where it actually uses the maintenance dose rather than the volume of distribution itself due to the way the drug's been being given. So if you put in, let's say around 110, you could put 107 if you want to be exact. Divide by 1 minus e to the Ke tau is around 847. I believe that's what we wrote over here too. Yep. That's around 126 milligrams when you do that calculation out. So you put probably a loading dose of what? Not 126, maybe 125 milligrams, followed by your infusion, intermittent infusion over an hour of 110 milligrams per hour. And that would get you each interval with a max and a min of 6 and 1 respectively. Finally, I just wanted to go over one more extravascular dosing example here, and this is on page 4. Page 4. And it says we have a long-acting form. We're switching from continuous IV to oral. We have a clearance that's here. We have a bioavailability factor we need to incorporate. Here's the tau, so it's BID, the SR tablet. And we want to have an average concentration of 5 milligrams per liter. And so if you go look at the equation, pretty straightforward. Times CL times tau over F, because we have to incorporate bioavailability. So that's looking like 5 milligrams per liter times clearance, which is 24 liters per hour, times tau, which is 12 hours. The hours cancel out, liters cancel out to leave milligrams on top, times divided by 0.85 to incorporate bioavailability. If you do all that math, we should be left with milligrams as our final unit. So 1694 milligrams. And what do you think? Do you think we'd give someone 1694 milligrams an oral drug? Probably not, right? So I'd have to tell you on the test to round it maybe to the nearest 1,000 milligrams. And what would that be? That'd be 2,000 milligrams or 2 grams Q 12 hours. There you go. That's how we use the extravascular steady state concentration equation on the last page of the equation sheet to figure out a regimen for someone that could be, for example, being switched from IV to oral. So I hope these problems help you get an idea of what you will be doing on the exam. Again, take these problems, change the numbers, give them to a buddy, see if you both get the answer. Go do my practice problems, go do all the videos. There's only so many ways that I can ask a question, but again, getting a question in a brand new form is where students get tripped up. So make sure you're ready with knowing your equation sheet really well, make sure you know your calculator really well, and make sure you're ready to identify the appropriate equations. Good luck.